Okay, so let's start off by recalling that in the previous analysis video, we ended the video with this result, which is known as the well-ordering principle. What it states is this: say you have a subset of the set of natural numbers x, which is a non-empty subset. Then there is precisely one element n in x which is less than or equal to all the elements of x. And this n is of course the minimum element of x, and it's denoted by min x. Now, if one goes back to the definition of the infimum of a subset of real numbers, then one will see that in this case, min x is in fact nothing but the infimum of x. So that is our well-ordering principle, whose proof we are going to see in one of the exercises at the end of this section. Now, the next result that we are going to see today, where we are starting things today, that tells us something about, again, a subset of the set of natural numbers, but this time not just non-empty, but additionally we are going to consider an infinite subset of n. So that is the next result, and we are going to do the proof of this one here itself, and in that proof we are going to use the well-ordering principle. So this is the next result. It's proposition 5815, and its statement goes like this: let x be an infinite subset of the set of natural numbers n. Then there exists a unique function which is a bijection. That means a one-to-one onto function. Unique bijection, let me write here, f from n to x, that is increasing that means as a function f is increasing, of course, in the sense that f of n plus 1 is greater than f of n for all n belonging to the set of natural numbers. So we have to prove this. If we have an infinite subset x of n, then there is a bijection like this, which is an increasing function, and only one such bijection, it's unique. It exists and it is unique. So let's see how we prove this, or how the author has proven it. Now there will be some issues in the proof which will be left unanswered. I mean, in the proof here itself, we will come across some issues which will be left unanswered here, but we will address them in one of the exercises. So that's how in fact the proof starts. So these are the precise words of Professor Tao. What he says next is this: we will give an incomplete sketch of the proof. with some gaps. Marked by a question mark. Like this, and these will be filled in the third exercise. Okay, so that's how we are going to go. So we ourselves will also not answer these places, these gaps here itself, but we will wait for the solution to that exercise where it is supposed to be done. So now in the beginning of the proof, I mean, this is just we are saying what we are going to do. Now the proof starts. In the beginning, what we do, we are going to define a sequence of natural numbers recursively, which will help us define that bijection f. So we define a sequence an of natural numbers recursively as follows. What is that recursive definition? By that definition, the first element of this sequence is a0, and in fact also recall that in a recursive definition, actually what we always do is we always define a sequence, not always of natural numbers. The objects in that sequence, that does not matter. I mean, their type is not restricted in the scheme of recursive definition, but we end up defining a sequence of some objects where they are labeled by natural numbers. Okay, so the first one is a0, and a0 is the minimum of our set X. Once the definition is given fully, we will then have to justify why it's a legitimate recursive definition. That we have to see. And in fact, for any natural number n, which if you want, you can simply just write this next thing that we are going to write instead of first writing this, but because in the actual recursive definition we first define the first element, so that's why I am writing it like this. You can just simply write a definition for an in general, that will include this one also. This is defined to be the minimum of this set, the set of all elements x in capital X, such that x is not equal to am for all natural numbers m less than n. Now the question is, there are some things we have to now see and make sure that whatever we have written here it makes sense and it's a legitimate recursive definition. We are writing minimum of x. Can we do this? Yes, we can, because you see, x is given to be an infinite subset of n, and as such it's in particular non-empty also. So by the well-ordering principle, x has a minimum element, and that minimum element is of course unique, and that is defined to be a naught. So a naught is nothing but the minimum of x which exists and is unique. Fine. But what about this one, an, where n in fact is any natural number? So I was saying just now that a naught, this definition is in fact contained in this. Is that really the case? What will you get if you put n equal to 0 here in this definition? According to this definition, you would get x is not equal to an for all natural numbers m less than 0. Okay. Now, is there any natural number m less than 0? Of course, there is no such natural number. So, what is it that we see here? Keep in mind that this condition can be written in a slightly different manner like this as an implication. If m is a natural number such that m is less than 0, then x is not equal to am. Now this is an implication whose hypothesis is this: m is a natural number and m is less than 0. And the conclusion of this implication is this. Is the hypothesis true? No. The hypothesis is false. So the implication is vacuously true. And vacuously true, that too, for what? For every element x in x, this is vacuously true. So that is why the set that we are looking at here, forget the minimum for a moment, just the set is nothing but the set of all elements x in x. That means this set is nothing but x itself. So that's why a naught, just like this definition, in fact by this definition also, a naught is the minimum of x. That's just the thing is, okay. So really this one is included in this. Okay, now we come to the general an. Does this definition make sense? It looks like a recursive definition. Why? Because you see that, say you have in fact defined a naught, a1, all these things up to say an minus 1. All these terms you have in fact defined using this definition. Now next you are going to define an. And what is the definition of an? In the definition, whatever the actual definition is, these previously defined terms are only used because you are considering the set of those elements in x, none of which is equal to these things. In other words, the element x in x belongs to this set if by definition of this set that x is none of these previously defined ans. So that means what we are looking at here is nothing but, I mean just the set is nothing but this. This. an is defined to be the minimum of this set. Okay, does that minimum exist? If so, is it unique? You see, X is given to be an infinite set, and from an infinite set, it does not matter how finitely many elements you remove, you are still going to be left with something. In fact, you are going to be left with still an infinite set. So that's why this is also a non-empty subset of what? Of the set of natural numbers. So by the well ordering principle, it also has a minimum, and that minimum is defined to be an. Okay, so our recursive definition not only makes sense, but it is genuine. Okay, it in fact gives us a well-defined sequence of natural numbers. So this part, of course, is only for our understanding. So after this, next it continues. Next part, the author writes, these things of course are written after defining this, that because of these reasons, this is a legitimate, a genuine recursive definition. But now come those parts where we will have question marks. One can show how, this is how a professor writes, that our sequence an is an increasing sequence. That is, A0 is strictly less than A1, which is strictly less than A2, and it goes like this. Okay, so we will have to prove this. And also, this next thing is that what am I looking at here? I was getting something else. And in particular, because this is increasing, in particular, an is not equal to an when the suffixes n and m are different. This fact is the consequence of this increasing nature, which also we have to prove. For all n and m belonging to the set of natural numbers such that n and m are different. And furthermore, there is one more fact, that is that these ans in fact all actually are elements of the set X itself. Also, an belongs to X for all n belonging to n. Where are the corresponding question? Okay, so here you have a question mark. How does this follow from this? And here also you have a question mark. Why is this so? So these are already we have we can see we are to address these three issues. But Still, let's just move on. Now we have our sequence. Now using this sequence we are going to define the actual function f. Now define f from n to x. You can pretty much guess how. By f of n equal to an. So you can now see that due to these facts, first of all, f in fact is a well-defined function. Why? That's because for each n there exists a unique an, and that's why f is well defined. But there is one more aspect to this. These ans in fact all are in x, so f is in fact a function from n to x. So we can write like this: by the observations in the previous paragraph, or if you want to be brief, you can just simply write by the previous paragraph. I am saying observations because we are yet to prove these things. Okay. F is well defined. But now something else also can be said about f. From this part, it directly follows that f is also one-to-one. Also, that if n and m are different inputs, then the corresponding outputs an and am are also different. For which n is not equal to m. That is, f is one-to-one. Okay, now to show that f is a bijection, we have to prove that it is onto. That means if we choose any element from our range x, then that element we have to prove equals an for some natural number n. So we will prove that by contradiction, by supposing that that does not happen. We next show that f is onto. Okay, so let x be any element in x. This x and the definition of an, that also has a set in which you are in. I think this will create a little bit of confusion. Let me call it y. Okay, let y be any element in x. So our supposition is this. Suppose y is not equal to am for all natural numbers n. This directly it just simply means that y does not have an inverse image in n under the function f. In other words, that f is not onto. That's what we are supposing. Then then y belongs to this set such that x is not equal to am for all natural numbers m less than n for all n. The question is how and why, and that is another issue which we have to resolve later on. So right now we just move on. We assume that yes, this is the case, and so we can use it. Now this implies what? Do you see what this set is? This is just the set that is there in the definition of the term an in our sequence. An is the minimum of this set, and y turns out to be an element of this set. Of course, under this supposition, fine, but still y is an element of this set and an is the minimum of this set. So this implies y is greater than or equal to an, simply because an is the minimum and y is an element in this set. But since an is increasing, our sequence is increasing, we have, again this is another issue, an greater than or equal to n itself for all natural numbers n. Okay, but how? Oh, I should have mentioned here also that this is happening for all natural numbers n. Pretty much here itself you can see that something is going to go wrong, so that we get our contradiction, because an is increasing. The terms of the sequence an are what? They are natural numbers. So we don't really know what natural numbers they are, but after all they are natural numbers and they are increasing, and y is a natural number which is greater than or equal to all of them, and that cannot happen. I mean, you can almost understand, but we still want to make it more clear, absolutely clear, that yes, we are finally getting to a point where we can see that we have obtained something which is absolutely impossible. So there we will get contradiction. That's why we are transitioning from an to n itself. Fine. Thus, so what do we now get? This is greater than or equal to an is greater than or equal to n. Thus, y is greater than or equal to n for all natural numbers n. But what is y after all? Y is in x, y is any element in x, and x is what? X is a subset of the set of natural numbers. So after all, y is itself a natural number. So in particular, you can choose y plus 1 in place of n, because y plus 1 is a natural number, and this is true for all natural numbers n. In particular, y is greater than or equal to y plus 1, which is not true, which is absurd. which is not possible, and this impossibility is stemming from our blind supposition. So the last supposition is false, that is y must be equal to am for some natural number n. Hence y is equal to am is what? Am is f of n, where m is a natural number. So we have now shown that any element y in our set capital X is an output for some input. Thus f is onto. So being one-to-one and onto, f is a bijection. Oh, did I forget to mention that f is increasing also? That just simply follows from the increasing nature of the sequence an. I think I did not write anything about that. So let me here make a short conclusion of what we have achieved so far. So f is a bijection. If I have in fact said somewhere before this that f is increasing in nature, then just ignore this next part. F is a bijection, that is increasing, i.e. f of n plus 1, which is an plus 1, is greater than an, which is f of n. For all natural numbers n. Now we are almost there. The only thing now we are yet to prove is that this f is unique. So suppose again that it is not unique. Now suppose there exists a bijection G from n to x that is increasing, but that is not equal to f. Such that g is different from f. As a function, g and as functions g and f are distinct. Then the set of all natural numbers where f and g vary, that is f of n is not equal to g of n, is a non-empty set, and definitely it's a subset of n. So we are now in a position to use the well ordering principle once more. Then the set is non-empty by the well ordering principle, its minimum exists. Let M be the minimum of this set. Okay, here there is no gap, but now the gap will come. This implies that f of what symbol has been used by the author. Oh, it's just simply okay. N is the variable here because m is this fixed thing. So f of m, or let me write like this because we know what f is. F is given by that sequence an, but we don't really know what g is. We have just supposed its existence. So g of m is not equal to f of m, which is, by the definition of f, this is am, and g of n is equal to f of n, which is an for all n less than m. What have we written here? You see, m is the smallest value of this set, and what type of set is this? This is precisely the set of those inputs where f and g differ. So m being the smallest element in this set is after all an element in this set. So at m also g and f will differ, and that's why we are having g of m not equal to f of m. In other words, g of m is different from am. But what about the smaller natural numbers? If there is any such natural number smaller than m, then due to the minimum nature of m, none of these n's belongs to this set. So for them, f and g will agree. Okay, so that's why g of n is equal to f of n, which is an for all inputs smaller than the minimum m. Here also there is no gap, but the gap comes next, where we use these things to ultimately conclude that g of m in fact has to be equal to f of m. But this implies that g of m is equal to the minimum of all elements x belonging to x, such that x is not equal to a, what symbol is he using? T. You can use anything, but he is using T. For all t less than m, which is nothing but, by the definition of our sequence, which is nothing but am, and am by the definition of the function f is f of m. But the question is how? How do these conditions, not this one of course, but these conditions imply that g of m should be equal to the minimum of this set? That is the question. But these equalities, of course, we understand. So this is in direct contradiction with this one, this thing, g of m is not equal to f of n. We thus have a contradiction. And so our last supposition is wrong. What was our supposition? Our supposition was that there is another function g like f which is different from f. Hence, f is unique. And this is where the proof ends. Ends in the sense we still have to address these issues, which we will do later on. Now, let me end things here itself, but before we really end the video, let's see what this result is telling us. What it says is that there is a bijection for any infinite subset x of the set of natural numbers. You can find a bijection between x and n, which is increasing, and such a bijection is unique. Let's just forget those aspects of this bijection. But the fact here is that such a bijection exists, which makes the cardinality of x the same as the cardinality of n. So if you want to have a subset of n whose cardinality is different from that of n, you can only consider finite subsets. If you consider an infinite subset, then in terms of cardinality you do not get anything new. You get that same cardinality back. So this is the, in this sense, this is the smallest infinity. That is, you cannot get any smaller. If you want to be smaller than the cardinality of n, you end up getting that same cardinality. You don't really get anything new. So this is the first infinity. There are higher infinities. We will see these things. And that's just it. The next video is on Tuesday, of course, coming Tuesday. And since we have already completed one cycle, yesterday, or I think day before yesterday, we saw graph theory. So this coming Tuesday, let's again go to group theory in Herstein's topics in algebra. So see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.